Hello everyone. So in the previous video we learned about the solution of Schrodinger equation. Okay. In this video we will learn what is radial wave function and what is angular wave function. Okay, so let's start. At first recapitulate some previous concepts. Okay. So we tell that minus h cut square by 2m into del square psi. So that means I am doing double derivative on psi with respect to x square, so del x square plus del square psi. So I am again doing the derivative on psi with respect to y square, so that's why del y square plus del square psi divided by del z square. So that means I am doing again derivative on psi with respect to z plus potential energy psi equals to total energy psi. Okay, so we told that this is the Schrodinger equation, and if we look at this equation, this is a differential equation, so the solution of this equation should be a equation, and as we are doing derivative on psi, our solution will come out as psi equals to, and I am doing the derivative with respect to x, so that should be equals to f of x. I am doing the derivative with respect to y, so that the solution should be function of x, y, and I am again doing the derivative on z by z with respect to z, so that's why this should be come out like that. Okay, now the question is, we are doing the derivative on psi with respect to x, we are doing the derivative on psi with respect to y, we are doing the derivative on psi with respect to z, so that's why our solution come out psi equals to function of x, y and z. Now the question is, what is psi? Why we are bothered about psi? What is the interesting matter about psi? Okay, so this psi is called wave function. Wave function. Now, so that means actually psi is a mathematical equation, and this mathematical equation is called wave function. Why this is called wave function? Because we all know that we when Schrodinger derived this equation, he considered the wave character of electron. So that's why the solution of this equation is called wave function. Okay, so this psi is called a wave function. Why this is called a wave function? Because when Schrodinger derived this equation, his equation, he considered that electron is a wave. Okay, we all know that electron has a dual behavior. It has particle nature, and it also has some wave nature. So that's why when Schrodinger derived this equation, he considered the wave behavior of the electron. So that's why this psi is called a wave function. Okay, now why we are interested on psi? Okay, now psi, the important matter about psi is that it helps us to know the probability of finding an electron around nucleus. Okay, so why we are interested on psi? That means why we are interested on wave function? Because it helps us to know the probability of finding an electron around the nucleus. The important matter in this sentence, the two things are very much important. I am telling that it helps us. Okay, so I am not telling that this will give the probability. I am telling that it helps us to know the probability, and I will explain it later on that why I am telling these kinds of things. So it helps us to know psi will directly not give the probability, but it will helps us to know the probability of finding an electron around the nucleus. Now another important term, I am saying that this is probability. So that means I am saying that psi cannot tell you the exact position or exact location of electron around the nucleus. It will only helps to know the probabilistic position of an electron around the nucleus, and it is quite understandable because according to the uncertainty principle, you cannot precisely say the position and momentum of a quantum particle. Okay, so that's why electron is a very much tiny particle, so that's why it is a quantum particle, so that's why we cannot precisely tell the position and momentum of this electron. Okay, so that's why we are using probability. Okay, so when we does not know the exact thing, we will use the probability. Okay, so that's why I am telling that the probability of finding an electron around the nucleus. Okay, now let's understand how psi will helps us to know the probability of finding an electron around the nucleus. Okay, so actually the mathematical form of psi is very much complicated, so that's why we need to understand this mathematical concept with a little bit easier way. Okay, so that's why I will not explain the mathematics detail, but what I will do, I will use some tricky ways to come to the results of the Schrodinger equations. Okay, okay, so at first consider a cubic region. Okay, okay, now let's say at the corner of this cube, at this corner of this cube or this cubic region, at this corner nucleus is present. Okay, so this is nucleus, so this is nucleus. Okay, now in this cubic region I am considering a axis. Okay, let's say a reference axis. Let's say this is my x direction, this is my y direction, and this is my z direction. Okay, so at first I am considering a cubic region, and at this cubic region, within this cubic region, at the corner of this cube, I am considering that nucleus is present here. Okay, now I am considering that the origin of I am considering the nucleus as origin, and I am drawing a axis. Okay, now let's say electron is present in the opposite corner, so this is electron. Okay, so let's say electron is present at the opposite corner, electron is present at the opposite corner of the cube. Okay, so that means this is the body diagonal. Let's say this body diagonal is r, so let's say the body diagonal is r. Okay, now in the x direction, let's consider this x, this length is x. In the x direction, let's consider this length is small x, and in the y direction, let's consider this length is y. So that means the edge length is y at the direction of y, and in the z direction the edge length is z. Okay, now I am considering the angle between r and z equals to theta. So angle between r and z equals to theta. Okay, so I am considering, at first I am taking a cubic region, and in this cubic region at the corner nucleus is present, and assuming that nucleus is the origin, I am drawing a axis, and this is x axis. I am assuming this is x axis, this is y axis, and this is z axis, and I am considering that in the opposite diagonal electron is present, so the distance from nucleus to electron is r. Okay, now I am considering that this direction is, this distance is x, this edge distance is y, and this edge distance is z. So why I am considering this? Because if you want to know the position of the electron according to the Cartesian coordination system, coordinate system, so that means at first we have to go in the x direction in this length, okay, along this length, and then you have to go to the y direction, the length y, and then you have to go in the upper direction, so that is the z direction, and you have to travel z length. Okay, so that means according to the Cartesian coordinate, the position of the electron is x, y, and z. Okay, small x, small y, and small z. Okay, now I am considering that the distance between nucleus and electron is r, and the angle between this distance r and z equals to theta. Okay, now I am taking, so now I am taking this line, I am drawing this phase diagonal. Okay, so I am drawing this phase diagonal. Okay, so let's say this angle is phi. Let's say this angle is phi. Okay, now I want a relation between x, y, z and phi. Okay, I am also drawing this body diagonal. I am drawing the, sorry, this is not a body diagonal, this is a phase diagonal. I am drawing the phase diagonal of this face and for the upper face and for this face. Okay, now I want a relation between x, y, z and r, theta, phi. Okay, now if you all know about the vectors, so it's very much easy. You can tell that if this distance from the nucleus to electron, if this is r, and the angle between z axis and r is theta, so then the z should be r cos theta. Okay, so from this picture, if this is r, so if this is r and the angle between z and r is theta, so that means the component towards the z axis should be r cos theta. Okay, so z equals to r cos theta. Okay, z equals to r cos theta. Okay, and what about this phase diagonal? Okay, what about this phase diagonal? If origin is o and this is let's say the point is p, so that means this op, that means this phase lower phase diagonal equals to r sine theta. Okay, so op equals to r sine theta. Okay, op equals to r sine theta. Okay, now if you do not know the concept of vector, okay, I will just quickly tell another way to find out this distance. Okay, so look at this rectangle. Okay, OP, let's say this is the point C where electron is present, and this is the point D. Okay, so I am considering OP CD rectangle. Okay, OPCD rectangle, and O and the dis, and in this origin nucleus is present, and at this C point electron is present, and distance between electron and nucleus is r. Okay, distance between electron and nucleus is r. Okay, now this OD is nothing but z. Okay, and the angle between r and z, that means angle between r and OD equals to theta. Okay, now if this angle is theta, so that means this angle also should be theta. Okay, this also should be theta. Now from the triangle ODC, I can write cos theta equals to So this is my hypotenuse and this is my base. Okay, so R is the hypotenuse and OD is the base. So base upon R. Okay, so OD is nothing but Z. So Z equals to R cos theta. Okay, now let's consider this. Okay, let's consider the triangle. Let's consider the triangle OCP. Let's consider the triangle. Let's consider the triangle. Okay, so let's consider the triangle OCP. Okay, from the triangle OCP I can write sine theta equals to perpendicular. So OP is the perpendicular. So the for the triangle OCP, OP is the perpendicular and OP is the perpendicular and R is the hypotenuse. So OP equals to R sine theta. Okay, so Z equals to R cos theta. What we are getting up to this, Z equals to R cos theta and OP equals to R sine theta. Okay, so OP equals to R sine theta. Okay, now the general concept is that the general concept for this is, let's say here is any vector A is present and this vector making an angle theta with this direction, let's say in the x direction and this y direction. So the component of A in this x direction is, so that means this A vector is making an angle with x, so that means along the x direction, so that means A vector is making the angle with x direction theta, so that means x equals to A cos theta and the component of A along the y axis, this should be equals to A sine theta. So with which angle so if a vector making an angle with x, making an angle with x, so that means the component along the x direction is A cos theta and component along the y axis is A sine theta. Okay, so that means cos component will be present along which direction, where where this vector makes the angle with the directional line. Okay, so now this OP is R sine theta. Now this OP is making angle theta phi with the x direction. So that means x should be equals to so this is OP and OP is making the angle phi with the x direction. Okay, so that means the length component of OP along the x direction should be the cos component. Okay, so that means x equals to OP cos phi. Now the value of OP is R sine theta previously determined. So R sine theta cos phi. Okay, now if this is x equals to R cos theta, then the y equals to so the y equals to OP sine theta, and if this is OP, so this is x equals to OP cos phi and y equals to OP sine phi. OP equals to y equals to OP sine phi, and the value of OP is R sine theta. So R sin theta sin phi. Okay, so this is coming out. Y equals to r sin theta sin phi. Okay, you can determine these things by considering the lower face rectangle. Okay, by the previous way. Okay, but if you know the vector, so it's very easy for you to determine. Okay, so now let's come to the results. So what we are getting? So we are getting the three important relation. What are the relations? I will write it again. It will be clear more. Okay, so what is the result? Three result we got, that z equals to r cos theta, x equals to r sin theta cos phi, and y equals to r sin theta sin phi. Okay, sin theta sin phi. Okay, y equals to r sin theta sin phi. So how we are getting this? I am considering a cubic region, and in this cubic region, in the one corner I am considering the nucleus, and at the opposite corner along the body diagonal I am considering the electron is present. Okay, and I am assuming a reference axis x, y, z, and assuming a distance from electron to nucleus r, and the angles theta with the the angle theta with between z and r axis, and phi is the angle between OP and x axis. Okay, so by considering these things I am getting the relation between x, y, z and r sin theta. I am getting a relation between cos theta sin theta cos phi and x, y, z. Okay, so by considering these things I am getting the relation between x, y, z and sin theta phi and r. So what is r? R is the distance from nucleus to electron, theta is the angle between z axis and r, and phi is the angle between OP and x direction. Okay, now what we are getting from this three, let's put these results on the wave function. Okay, let's put this result on the wave function. So from the solution of these equations, what we are getting? We are getting the psi. Okay, now what we will do, we will put these values on psi. Okay, so if I solve this equation, what I should get? I should get the wave function, and my wave function equals to function of x, y, and z. Now I am getting x equals to, so function x equals to r sin theta cos phi, comma, y equals to r sin theta sin phi, and z equals to r cos theta. Now look at the functions of psi. Now the psi depends on r. So what are those parameters which are present within the bracket? So in the previous video we told that within the bracket the independent variables are present. Okay, so in this expression within the bracket, which parameters are present? In the previous equation, x, y, z are the independent parameters, but considering a cubic region and considering and doing some little bit mathematics, we are getting this relation between angle and the x, y, z Cartesian coordinate distance. We are getting these three relations. I am putting these three relation on the psi, and I am getting r sin theta sin phi, r sin theta r sin theta cos phi, r sin theta sin phi, r cos phi. Okay, so in this independent variable region, now instead of x, y, z, I am seeing r, theta and phi in the form of some trigonometric function. Okay, so that means now my psi will depends on theta, phi and r. Okay, so now I can write this equation. I can write this psi in this form, and also I can write this psi with a little bit short form, which means now my psi will depend on theta, phi and r. Okay, so that means I will write sin phi is the function of r, theta and phi. Okay, now I will write this as r, theta, phi. Okay, so what we are doing here, what we have done, so at first I am getting this wave function, and this equals to the wave function psi equals to function of x, y, z. Then I am determining the values of x, y, z by considering a cubic region and considering a reference axis. I am getting the values of x, y, z with the distance between electron and nucleus and angle theta and phi, with the angle theta and phi. Now I am putting these relations on the expression of wave function, and I am getting that psi equals to function of x, y, z, and within this independent variable region I am putting the values of x, y, z. I am getting f equals to psi equals to function of r sin theta cos phi, r sin theta sin phi, r cos theta. Okay, now psi equals to function of r theta. Now if I want to write this expression in a shorter form, then so from this expression it is clear that the psi will only depends now the in the previous case the psi will depends on the x, y, z, but in this case I am substituting x, y, z by r theta phi, and I am in this expression it is clear that if I substitute the values of x, y, z, so it is clear that now psi will solely depends on r, theta and phi. Okay, r, theta and phi, because in this equation we are seeing all r simple r sin theta cos phi, sin theta sin phi and cos theta. Okay, so if I want to write this expression in a shorter form, then I can write that simply psi equals to function of r theta phi. So that means now the values of psi will depends on r, theta and phi. Okay, so this is another representation of a wave function. Okay, and this is more applicable and general wave function. Okay, now let's go to a different point of view. Okay, so now what we will do, we will use a mathematical tools called separation of variables. Okay, so this is not very much difficult, very much easy thing. So if I tell you z equals to xy minus x minus y plus 1, so that means here from this equation I can write z equals to f of x comma y, because from this expression it is clear that z depends on the value of z depends on the x and y, so that's why z equals to function of x and y. Okay, now let's rearrange this equation little bit. Okay, so this should be y minus 1 minus 1 I am getting here, so this is like expression. So if I take y minus 1 common, so this is x minus 1. Okay, now look at this equation, this y minus 1, this term only depends on y, so I can write this is f of y. Okay, now this term fully depends on x, so I can write this is f of x. Okay, so at first my expression was z equals to function of x. Now by doing some little bit rearrangement I am getting, so At the initial form, it was z equals to function of x comma y. Now by doing a little bit rearrangement, I am getting z equals to function of x into function of y. So what is happening here? So at first z equals to function of xy. Now this function of xy, this is equals to function of x into function of y. So I am separating x and y as a two different function. Okay. So initially by looking this equation, I am thinking that z depends on x and z also depends on y. So is a function of x and y. Now with little bit rearrangement, I am getting that z equals to function of y into function of x. So function of x comma y equals to, I am getting function of x comma y equals to function of x and function of y. So I am just separating these two variables in a multiplication form. Okay. So this is called separation of variables. Okay. But this is not always applicable. Okay. All function will not show this property. Okay. So if I apply, so from this example, it's clear that if the function of x comma y can be written as function of x into function of y. Okay. So I will just use this property in case of the wave function. Okay. So okay, so psi equals to function of r theta phi. What is r? R is the distance of electron from the nucleus. Theta is the angle between the r and z axis, and phi is the angle between x axis and r. Okay. Now so psi here, psi equals to function of r theta phi. Okay. Now if I do the separation of variables like that, if function of x comma y can be written as function of x into function of y. So now this part, this is the psi equals to function of r theta phi. So if I do a separation of variables, phi equals to function of r theta phi. So I can write it function of r into function of theta comma phi. Okay. Someone can tell that why you are not separating these two. So function of r, so you should write that function of r into function of theta into function of phi. Okay. This is also correct, but I am not separating these two because this r is the distance from nucleus to electron, and this theta and phi both are the angles. So that's why I am separating distance and the angles. Okay. So that's why doing the separation of variable, I am getting function of r into function of theta and phi. This function of r sometimes written in the book as this. So look at this function. Okay. So this function totally depends on the distance from the nucleus to electron. So r is the distance of electron from the nucleus, and this function f of r only depends on r. So that means this function only depends on the distance from the nucleus to electron. So that's why this function only depends on r. So that's why this f of r is called radial wave function. This is called radial wave function. Okay. This is called radial wave function. Okay. Now this f of theta and phi, so this function only depends on angle. So that's why this f of theta and phi is called angular wave function. Now in books, this f of r is written as r of r, and in case of the angular wave functions theta and f of theta and phi, this is written as y of theta and phi. Okay. So y of theta and phi, like that. Okay. So this is the bookish term. Okay. So f of r, this functional term, the distance from so this radial wave function, is written like r of r in the books. Okay, so this is same. The f of r and the r of r are the same things. Okay, this is called radial wave function. In the books, they prefer to write in this form. Okay, so f of r is equivalent to r of r, because this is the bookish terminology, and f of theta and phi equivalents to y of theta and phi. Okay, so this is called radial wave function, and this is called angular wave function. So what we have learned that if we solve the Schrodinger equation, we are getting psi is the function of x, y, z, and if we substitute this x, y, z by this equation, by these three equations, okay, considering a Cartesian system where electron and nucleus are present, and if we put these three equation on this on psi equals to f of x, y, z, in this equation, if we put the values of x, y, z, we are getting that psi is also the function of r, theta and phi. Okay, now doing the separation of variables. Okay, so I am this is the function of r, theta, phi, and I am separating the variables and telling that f of r into f of theta and phi. Okay, so I am doing the separation, I am operating on separation of variables on psi, and I am getting f of r, I am writing f of r into f of theta and phi. Okay, and as this f of r is only depends on the distance between nucleus and electron, so this wave function f of r is called radial wave function, and this part f of theta and phi only depends on angle, so this is called angular wave function. Okay, and in the bookish language, this f of r written as r of r, and this f of theta and phi written as y of theta and phi. Okay, both are the same. Now we all know that to represent an electron we need 4 quantum numbers. Okay, we all know that for the representation of an electron we need 4 quantum numbers. Okay, first one is a principal quantum number, second one is azimuthal quantum number, third one is magnetic quantum number, and fourth one is spin quantum number. Okay, so if we know the basic concept of atomic structure, then we all know that for an electron, for the specification of each electron, we need 4 quantum numbers, and these quantum numbers are principal quantum number, azimuthal quantum number, and magnetic quantum number, and spin quantum number. Okay, so what we have learned that the wave function, if I solve this equation, I will get function of x, y, and z, this equation. So from this seeing this equation, I can tell that the solution of this equation equals psi equals to f of x, y, z. I am considering a cubic region where electron is present on the corner of a cube, and the opposite corner electron is present, and so I'm doing little bit mathematics with the coordination system. If I put the values of x, y, z, I will find that this also written as r, theta, and phi, and after doing the separation of variables, I am getting f of r and f of theta and phi, where f of theta in the bookish language written as r of r, which is called radial wave function, and this is written as y of theta and phi. Okay, so this is called radial wave function, and this is called angular wave function. Okay, so this angular wave function and this radial wave function, so that means that the wave function is made up of 2 parts. One is angular wave function and one is radial wave function. Okay, so from this all discussion, we all know that we have learned that psi is made up of 2 parts. One is angular wave function and another one is radial wave function. Okay, now we all know that for the specification of the electrons we need 4 quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. Now this r of r That means the radial wave function only depends on n and l. So that means principal quantum number and azimuthal quantum number. So that's why sometimes in the book this is written as nl. Okay, this is written as nl. Okay, and this angular wave function only depends on azimuthal quantum number and modulus of magnetic quantum number. Okay, so that's why sometime in the book the angular wave function is written on like that, L mod of m. Okay, angular function is written like that, mod of L and mod of m. Okay, so what we have learned that if we solve the Schrodinger equation, we will get a wave function that is the function of x, y, and z. And if I consider a cubic region and consider some little bit mathematics, and I will get that this f of x, y, z also equals to r theta phi, f of r theta phi. And doing the separation of variables, so that means f of r theta phi, I can write f of r into f of theta into f of theta and phi into f of theta and phi. And this f of r is called radial wave function, sometimes written as f of r, and this f of theta and phi is called angular wave function, sometimes written like y of theta and phi. And as this radial wave function only depends on principal quantum number and azimuthal quantum number, so sometimes this kinds of notation is used, r of nl, r nl of r and y lm of theta phi. Okay, so that means angular wave function is, so what is the meaning of this notation? The angular wave function only depends on azimuthal quantum number and magnetic quantum number, and the radial wave function only depends on principal quantum number and azimuthal quantum number. Okay, now so from this concept we can from up to here we can learn now in from this expression we can say that the values of psi can be 0 if radial wave function is 0. So let's say the values of radial wave function is 0. Okay, let's say the values of radial wave function is 0. Okay, so then psi will be 0, and if the angular wave function will be 0, so then psi will also 0. So psi can be 0 by two cases, where radial wave function is 0 but angular wave function is not, so in that case psi also 0. And if angular wave function is 0 but radial wave function is not, at that case also psi is 0. Okay, so this concept, from this equation we can introduce the concept of nodes. Okay, but we will do it in the we'll do it in later. Okay, we will do it in the next videos. Okay, so thank you everyone.